equal to 0. Now, to be careful here, I don't have a no-go theorem. If fy is equal to 0, that doesn't actually prove that you can't write y as a function of x. It's just I can't be sure you can write y as a function of x in that context. But where there's smoke, there's fire, you know? So like, for example, if I have x squared plus y squared equals to r squared, right? This is my level function. What's partial f, partial y? 2y. Very good. So you think about the circle, right? Think about x, think about y, right? You guys can see, of course, we can't solve for y as a function of x here on an open set around the point, right? I mean, so, you know, again, this showing that partial f, partial y is 0 at this point doesn't prove that you can't do it, but in fact, it's often the case that it is in fact true that you can't do it. It's the case here, right? We can't solve for y as a function of x on an open set near the intersection point because you go above and below and the vertical line test fails, right? Because I have both y equals to the square root of r squared minus x squared and minus the square root of r squared minus x squared on those kinds of open intervals about the point r0 or minus r0. That's the implicit function theorem. So it's not too big a sin, really, in Calculus 1 to just tell students you can solve for y as a function of x. Because locally, you can usually do it, right? This implicit function theorem, though, is pretty awesome because it even allows you to say things that you can decide that you can solve for y as a function of x, at least locally, even if you have no hope of actually doing so. So, for example, y to the 6th plus 4 y to the 4th plus y squared minus x cubed equal to 0, right? Can I solve for y as a function of x? We could decide that, right? This is my level function f. And so like partial f, partial y. Oh, I did a bad thing. I'll tell you, y to the 5th, y to the 5th. There, I feel better now. All right, so 5 y to the 4th plus 16y cubed plus 2y, right? So, you know, this equal to 0, believe it or not, is something you could solve if you had enough time. There is a solution for a quartic. Like fourth order equations have general solutions. But here's the rub. It may or may not be possible to solve for y to the 5th explicitly in terms of algebra. We don't have a quintic formula. But if this is not equal to 0, let's say, right? If this is not equal to 0, then that means that y is equal to some function of x. You know, can know, even though can't find. Actually find it, right? This is an existence theorem. All right. Let's see here. All right. So we are near the next section, which is on gradients in other coordinate systems. I'll do that tomorrow. I'm not going to try to rush it right now. So we have time for one more example, which I think will be interesting for you. Suppose you have an ant. How many ants? How many legs do ants have? It's got 6? 6 x, okay. Imagine that's an ant. And it's constrained to x squared plus 2y squared plus 3z squared equals to 1 for z greater than or equal to 0. So it's stuck on the upper half of this ellipsoid, right? If dx dt is equal to 1 centimeter per second, and dy dt is equal to 2 centimeters per second, then how fast, in other words, the speed, is Mr. Ant walking? So at this point, I just kind of left the partial differentiation discussion we've been having today and just shifting gears a bit here for an example. So let's let, x of t, y of t, z of t equal the position of Mr. Ant, right? What do we get to say? We get to say that f of r of t is equal to what? Oh, I'm sorry, I didn't tell you what f was. What was f? This thing is the level function which it's stuck on, right? So I know that f of r of t is equal to? It's equal to 1 by assumption, right? But let me just be a little bit more explicit. So we know that x squared plus 2y squared plus 3z squared equals to 1. I mean, I think we can all agree that. But here what? X, y, and z are functions of t. So these rates of change are constrained by this level equation, right? If I take the, check this out. Here's another way of thinking. 2x dx plus 4y dy plus 6z. Don't tell the other math professors I did this. dz equal to 0. If you take that equation and you divide it by dt, in fact, that is the chain rule for a function for Mr. Ant's motion. If you compose the position of Mr. Ant with the ellipsoid equation, and then you differentiate that, the chain rule says this. But you know what? You could also just take the total differential of the equation and divide by dt. You get the same thing. This method of differentials is unreasonably effective. But, okay, so you can solve for dz dt. What is dz dt? Oh, I see I've forgotten something, which is what? The point Mr. Ant was at, right? What point do we want to put him at? I guess we could leave it, let's leave it symbolic since I'm almost out of time. So we got minus 2x times what's dx dt? 1 centimeter per second, right? Minus 4y times 2 centimeters per second, all divided by what? 6z. So this gives you the z component, and then to find the speed, what's the speed? So dx dt is given to be 1 squared plus 2 squared plus Pac-Man squared. Let's call this thing Pac-Man. And that would be the speed. Anyway, all I'm trying to tell you guys is a simple thing, is if you're constrained to a surface, right, then you don't really have 3 independent variables. You've got 2, which you could write in terms of the, you can write one variable as a function of the others, provided you've met the implicit function theorem test, basically. And so if I give you the speed of 2 of the Cartesian variables, the third one's automatically pinned down because of the relation of the level surface, right? In other words, these rates are related. Right? This is the related rates problem we do in Calculus 1, where we make students partial differentiate without teaching them partial differentiation. Oh, the horror. But yet somehow you guys do it in Calculus 1 without ever being taught it, right? It's interesting, isn't it? Okay, anyway, I shut up. I'll see you guys tomorrow.